Hey guys, welcome to my channel. This time I'll be discussing the so-called Cramer's rule. Cramer's rule is actually a way of using matrix determinants to solve a linear equation system. So let's get started. Let's have an example of a linear equation system consisting of three equations with three variables. Suppose that we have this kind of linear equation system. In algebra, we can solve this kind of linear equation system with three equations and three variables using elimination and substitution method. The first thing we need to do in the Cramer's rule is that we put all the coefficients of the equations into a matrix form. Remember, it's the coefficients that we put into the matrix. Suppose we call it matrix A for our purposes, so we put all the coefficients of the equations into this matrix. We have put all the coefficients of variable x, y, and z, and also the result coefficients into their respective column of the matrix. So the first column of the matrix represents coefficients of the variable x, and the second column for variable y, and then the third column for variable z, and the right-hand side column of the matrix represents the result coefficients. There you go guys, all the coefficients of the linear equation system into the matrix. We call the resulting matrix the augmented matrix. The next step in the Cramer's rule is that we calculate the determinant of the left-hand side of the matrix, which is the square 3 by 3 matrix. In this step, we have to exclude the result coefficients for the time being. This is actually an important step in the Cramer's rule. So once again, we have to exclude the result coefficient column on the right-hand side of the matrix. In that case, we need only to focus on the square 3 by 3 matrix on the left-hand side. For the calculation of the determinant of the matrix, I'm using the Saurus rule. If you want to know in detail how the Saurus rule works, you can check the reference site below. In applying the Saurus rule, first we copy the square 3 by 3 matrix out of our initial matrix. Then we also need to copy the first two columns of the matrix and use them as the fourth and the fifth column respectively. Now we can start the calculation of the determinant of the matrix. First, we have to calculate the sum of the products along the downright diagonals as represented by the yellow arrows. And here is the sum of the products along the downright diagonals. Next, we need to subtract the sum of the products along the upright diagonals as represented by the red arrows. Here is the sum of the products along the first upright diagonal. And don't forget to put the minus sign before the opening bracket because it is a subtraction. And here is the sum of the products of the second upright diagonal. And this is for the third upright diagonal. Then we've got all the sums of the products of all the diagonals here. There you go. In this case, we've got minus 2 as the determinant of the matrix. In other words, you can also say that the determinant of our example of linear equation system is minus 2. Now we're moving on to the calculation of the determinant of each of the variables. We can start with variable x first, although we can actually start with any other variable as well. So let's choose to calculate the determinant of variable x first. So we're back to the initial matrix A first. So first we have to replace the x coefficient column with the result coefficient column. This is actually the key step in the Cramer's rule. And we will see later on, we will do the same for variable y and variable z as well. So what we've got here as a result is a square 3 by 3 matrix. And again, we will use the Saros rule to calculate the determinant of x variable here. And again, we need to copy the first two columns and use them as the fourth and the fifth column respectively. Now we are ready to apply the Saros rule. And as we did before, we need to calculate the sum of the products along the downright diagonals as represented by the yellow arrows. And the products along the downright diagonals are listed here below. Then we need to subtract the sum of the products along the upright diagonals, as represented by the red arrows. And because it is a subtraction, don't forget to put a minus sign before the opening bracket. So as a result, we've got the determinant of variable x, which is in this case minus 38. Now we have calculated the determinant of the matrix and the determinant of variable x. At this stage, we can actually solve for x. In this case, the formula for x is the determinant of x divided by the determinant of matrix A. So first, the determinant of x is minus 38, and the determinant of matrix A is minus 2. Next, the formula to solve for variable x is the determinant of x divided by the determinant of matrix A. So we put all the numbers into the formula. Then we've got minus 38 divided by minus 2, which is 19. There you go, guys. As you can see, we have solved for x, which is 19. Okay, guys, we're moving on to the next step. We're back to the initial matrix A, and then we can calculate the determinant of the other variables. As we did previously for variable x, we will do the same for variable y. First, we need to replace the y coefficient column, which is the second column of the matrix, with the result coefficient column, which is on the right-hand side of the matrix. As you can see here, we have replaced the y coefficient column with the result coefficient column. And then we need to copy the first two columns of the matrix and use them as the fourth and the fifth column respectively. Then we are now ready to calculate the determinant of variable y. Again, I'm using the Saros rule to calculate the determinant of variable y. So first, we calculate the sum of the products along the downright diagonals as represented by the yellow arrows. And here are the numbers. Then we need to subtract the sum of the products along the upright diagonals as represented by the red arrows. And the numbers are listed here below. And because it is a subtraction, don't forget to put a minus sign before the opening bracket. And here are all the sums of the products of the diagonals. There you go. We've got the determinant of variable y, which is 8. Now we are ready to solve for variable y. So in this case, variable y is defined as the determinant of y divided by the determinant of the initial matrix A. So the determinant of y is 8. Then the determinant of matrix A is minus 2. And the formula for y is defined as the determinant of y divided by the determinant of matrix A. So putting all the numbers into the formula. So y is 8 divided by minus 2. Then we've got y is equal minus 4. So guys, we have solved for variable y. In this case, y is equal minus 4. Okay guys, we have solved for variable x and y, and now we're moving on to the next step. We're going to calculate the determinant of variable z. And now we're back to the initial matrix A first. As we did previously for variable x and y, we will do the same for variable z now. First, we have to replace the z coefficient column, which is the third column of the matrix, with the result coefficient column, which is on the right-hand side of the matrix. There you go. We have replaced the z coefficient column with the result coefficient column. And again, we need to copy the first two columns of the matrix and use them as the fourth and the fifth column respectively. And again, I'm using the Saurus rule to calculate the determinant of variable z. And then we have to calculate the sum of the products along the downright diagonals as represented by the yellow arrows. And here are the numbers. Then we need to subtract the sum of the products along the upright diagonals as represented by the right arrows. And here are the numbers. Don't forget to put a minus sign before the opening bracket because it is a subtraction. There you go. We've got all the sums of the products of all the diagonals. And then we can calculate the determinant of variable z, which is minus 12. Now we are ready to solve for variable z. In this case, z is defined as the determinant of z divided by the determinant of the initial matrix A. We are going through the calculation step by step. First, the determinant of z is minus 12. And the determinant of the initial matrix A is minus 2. Then we've got the formula to solve for variable z, which is defined as the determinant of z divided by the determinant of A. So putting all the numbers into the formula, z is minus 12 divided by minus 2. Then we've got z is equal 6. There you go guys, we have solved for variable z. Okay guys, here is the summary of the solutions. So variable x is 19, variable y is minus 4, and variable z is equal 6. Okay guys, we have basically finished our example here. Now we can summarize the steps in this Cramer's rule. First, put all the coefficients of the linear equation system into a matrix form. Then calculate the determinant of the square matrix on the left-hand side. The next step is calculate the determinant of each variable. First, replace the variable coefficient column with the result coefficient column. And then calculate the determinant of the resulting square matrix. Then solve for each of the variables using the formula which is defined as the determinant of each variable divided by the determinant of the entire linear equation system. Okay guys, that's all for now. Don't forget to subscribe and give a thumbs up to this video. Thanks for watching.